differentiation. So firstly, let's say we have a straight line, right? Straight line. And we know that's given by y is equal to mx plus c, where m is the gradient of the line. We already know this. But what if instead we had a curve that looks something like this? Went down and then went back up, right? Let's say that's a curve that we had. Does this curve have a gradient? Or what does it mean for a curve to have a gradient? Is that a thing? Does it make any sense? Well, the answer is yes and no. So the curve does not have a gradient, but each point on the curve has a different gradient. So let's say we have this curve, right? We'll choose our own example. Let's say we have let me draw that better. Let's say we have y is equal to x squared plus 2x minus 3, right? I can tell you it's going to look something like this. Something like that. And to get the gradient at each point, what we can do is draw a tangent. So let's say this is x is equal to minus 5, let's say, right? What we can do is draw a tangent to the curve at that point, and a tangent is just a straight line that touches the curve at that particular point. So let's say that's our tangent. Imagine that's a straight line, and let's say this is where x is equal to 2, and that's our tangent. Let's say that's what the tangent looks like. It's not perfect, but the idea is that these two tangents obviously have different slopes. This one's clearly negative, this one's clearly positive. And of course, if you draw a tangent at this point, it's going to have a different slope than any of these two tangents. So how can we know what the gradient is at that point? Well, we use something called derivatives. Derivatives. And what we have is a power rule. This is the easiest way to take derivatives. Power rule. So let's say we have, let's use this function, yeah. Let's say we have y is equal to x squared plus 2x minus 3. So how do we find the derivative? Or you could say derivative, you can remember this as like the gradient function. Because all the derivative does is it gives you the gradient at a certain point on the curve. So the way you take the derivative is you see the power on x squared. That's 2, right? This is 2 right here. So you do 2, you multiply it by the coefficient of x squared, which is just 1, because nothing there means just 1. So that's 1. And then you have x squared again, but then you reduce the power by 1. So you make it 2 minus 1. And then you add that, and then you do the same thing for the second term. So you have, so the power on x here is just 1. So you have 1 times, the coefficient of 2x is just 2. And then x to the power 1 minus 1 again. Minus 3 times, okay, so this is nothing here, which is the same as x to the power 0. That's what the power is. So you can do 3 times 0, x to the power 0 minus 1. Of course, this is going to cancel out. So we'll have 2 times 1 is 2, times x to the power 2 minus 1, which is just 1. So we have 2x, plus 2 times 1 again is 2. X to the power 1 minus 1 is x to the power 0, which is just 1. So plus 2 times 1. And then this is minus 3 times 0. So this is just 0. So we don't need to add that. And then you're left with 2x plus 2. So the gradient function is equal to 2x plus 2. But gradient function is a long word, and instead of saying that, we just say dy by dx. Or you'll see written as y prime, or you might see written as f prime of x. All of these mean exactly the same thing. This means take the derivative of the function that you have. Alright, so let's do a worked example and it'll make more sense. So we have the question, f of x is equal to x cubed minus 3x squared minus 4. Find the gradient of the graph of y is equal to f of x, where x is equal to 1. Well, we know how to find the gradient, right? The gradient function is just dy by dx, which is also the same as f prime of x. Well, we know what to do now. Let's start with x cubed. So we have 3 right there. So we put the 3 in front, multiplied by the coefficient of x cubed, which is just 1. So that's 1. And then x to the power 3 minus 1. So that would just be 2. Minus, well, we take the power again. That's 2. The 2 comes from here. Take the 2. Multiplied by the coefficient, which is 3. And then x to the power 2 minus 1, which is just 1. And then minus 4, and then of course this is x to the power 0 again, as we said. So this is 4 times 0, x to the power 0 minus 1. We don't need to worry about this because it will cancel out. And we're left with f prime of x, which is the gradient function, is equal to 3x squared minus 6x to the power 1, which is this minus 6x. So find the gradient where x is equal to 1. Well, so you put 1 instead of x squared here, and you put 1 instead of x over here. So you're left with 3 times 1 squared minus 6 times 1. That's just 3 minus 6, which is negative 3. So look, instead of drawing the whole curve, which would probably look something like, I don't know what it looks like. Let's just say it's a cubic, so it looks something like that. And you'd have to find x is equal to 1, and you'd have to draw the tangent, and you'd have to make sure that your tangent is precise as well. And then you'd have to make sure that you calculate the gradient. Instead of doing that, we can just take derivatives and get the actual answer, which is correct and much cleaner. Find the coordinates of the turning points of the graph y is equal to f of x. Okay, so what are turning points? So, by the way, if you hear turning points, stationary points, critical points, all of them mean the exact same thing. So, turning point. So let's say we had a curve that looked like this. Let's say we had a curve that looked like that. You can see at this point right here and this point right here, right? Let's say we wanted to draw a tangent at those points. Well, the tangent would just be a horizontal line, right? It's a horizontal line. It's a horizontal line. What does a horizontal line mean? We know this from, previous work with lines. Horizontal line means, well, it just means that the slope or the gradient is equal to 0. But we know how to get the slope. The way to get the slope is by taking the derivative. Well, we already took the derivative. Our derivative is 3x squared minus 6x. And it has to equal to 0 at the turning point. Well, it's equal to 0. That's it. That's all you have to do. And now you just have to solve this equation for x. Well, you can divide by 3, so you're left with x squared minus 2x equals 0. And then you can factorize. You have x minus 2 equals 0. We can have x is equal to 0 or x is equal to 2. And then you have to find the coordinates, right? So you put x is equal to 0 back into the function f of x. So you put it back into this function right here. So you would have 0 cubed minus 3. That's 0 cubed minus 3 times 0 minus 4. I think that's what the function was. Yep, minus 3 times 0 squared minus 4, which is just negative 4. And then when x is equal to 2, you would have 2 cubed minus 3 times 2 squared minus 4, which is equal to 8 minus 12 minus 4, which is equal to negative 8. But that's it. Those are your coordinates. You have 0 and minus 4, negative 4. And then you have 2 and negative 8. And you have to make sure that you match the correct coordinates. You can't do 2 and negative 4. You can't do 0 and negative 8. You have to make sure that you match what's happening. Let's do a bonus section actually. Let's call this bonus. So we know how to take derivatives. We know what they do. They give us the gradient at any point. And we know that can help us find the turning points on a curve. But what if you want to know if the turning point is a maximum or a minimum, right? Well, in this curve, it's pretty simple. You can see this is like a maximum point because it's pretty high up. This looks like a minimum point because like at the bottom. But what if the curve was more complicated and we couldn't draw it? How would we know how to get the nature? It's called the nature. How would we know what the nature of the stationary point is? Well, what we do is we take the second derivative. So you write it as d squared y by dx squared. That's just the notation. Or you could write y prime prime or f prime prime of x. And all it is, yeah, you just take the derivative of the derivative that you already have. So in our case, our derivative was 3x squared minus 6x. So we have to take the derivative of 3x squared minus 6x. Well, that's pretty simple. We know how to do this. So we do 3 times the power 2 right here times x to the power 2 minus 1, which is 1, minus 6 times 1, which is the power here, times x to the power 1 minus 1, which is 0. And you're left with 6x minus 6. And now what we do is we put our x coordinate back into the x over here. So we put it back in. So now we have 6 times 0 minus 6, which is obviously negative 6. And then we have 6 times 2 minus 6, which is positive 6. That's a 0. And this is just something you have to remember. Maybe a proof will be in a different video. But if the second derivative, so this is the second derivative, right? If it is less than 0, then this is a maximum point. You have to remember this. And if it is greater than 0, then it is a minimum point. Something you have to remember. If it is equal to 0, then it's called an inflection point, but I don't think we need to worry about that right now. It's called a point of inflection. But honestly, don't really think about this. We don't need this right now. We just need this, and we need this. So now we don't even know what this curve looks like, but we know 2 things about it. We know it has 2 turning points at 0 and negative 4. So let's try to draw this curve, even though we don't know what it looks like. Let's make it cleaner. So 0 and negative 4, there's a turning point there. And 2 and negative 8, there's a turning point there. So that's 2, that's 0. Well, we know the point at 0, negative 4 is going to be a maximum, right? Because when you put 0 and you go to a negative number, and that means maximum. So that means it's going to look something like, it's going to be coming upwards at this. And then since 2 was a minimum point, that means it will be going downwards at this point. And since it's a cubic, it has this type of shape. So we know it's going to look something like that. And we have a pretty good sketch of this curve, even though we have no idea about anything related to this curve. But still, by just getting the turning points, we can draw a pretty good sketch of this curve. And if you draw the actual curve on, let's say, GeoGebra or whatever website you use, you will see it looks similar to this. There's going to be an x-intercept somewhere over here, but we don't know what it is. We don't need to find that right now. So in conclusion, what have you learned? So we have, let's write over here. So we know about derivatives. That's the main thing. We know that it's basically the gradient function. Gradient function. We know how to calculate it using the power rule. Power rule. We know about turning points or stationary points, critical points. And the bonus section that if you stayed for, you learn about the nature of turning points. You know about nature of turning points and derivatives, gradient function, power rule, and that's all you need to know for an introduction to differentiation.